Symmetry.
Yeah, so it's great to be here. Thank you all for staying for the end. It's been really fun getting to know so many new folks and seeing some old friends. So I'm going to kind of continue with a lot of the lines of discussion around symmetry, equivariance. How is this helpful for doing machine learning on atomic systems? So I'm going to kind of give my view on Euclidean symmetry and its importance for atomic systems and doing making models for them. And also show some applications. So, how effective are these methods, and maybe share some of the kind of fun properties of these networks if we have time. So this is sort of just a teaser graphic, and I'll explain it in a little bit. Okay, so I'm just going to kind of, if you get any takeaway from this, it's that geometry and symmetry are fundamental and powerful assumptions for building models of physical systems, especially atomic systems, but I think this really it's not scale dependent. And one of the reasons, there's many reasons why you might want to build symmetry into your models. The one that's my personal favorite is that coordinate systems are fundamentally arbitrary, and we don't really want our model to be biased by them. And so to make that a little bit more concrete, let's say I have some atomic system, these 3 benzene molecules, and in order to describe to a computer where these benzene molecules are, what are they doing, I typically have to lay down some sort of coordinate system, some arbitrary coordinate system, so it could be either coordinate system 1 or 2, and those descriptions look different when I write them down on a piece of paper or put them into a computer, but they really mean the same thing. So how can I use the fact that coordinate systems are very useful for describing things but not be biased by it? So if I were to kind of give these 2 descriptions of this system to a traditional neural network, it's like, okay, these things are totally different. They're not related. You have to basically kind of train it to sort of learn to give similar outputs or related outputs. So what a lot of people do is they say, you know what, coordinate systems are really inconvenient. Let's get rid of them. So let's describe things in terms of radial distances and bond angles, and that's all well and good. You won't be able to tell the difference between the description 1 and 2. You also lose a lot of geometric information. So equivariant models keep the coordinate system around, and those models understand that the description from coordinate system 1 and coordinate system 2 are in fact describing the same thing, and that any outputs of the network should transform accordingly to my coordinate change. Just to kind of hit home why this might be desirable to not go the traditional route and do data augmentation, this has kind of been discussed a lot in other talks. Data augmentation, particularly in 3 dimensions, is very expensive. So if we're just talking global equivariance or like global rotations, not, there's also local rotations of features and stuff, so it gets even more expensive. But in 3D, you need about 500-fold augmentation on your training data in order for something to understand, for example, that this cube is the same cube, just in different orientations. It's just showing 100 snapshots, so you'll need a lot more than that. Versus if I'm training with symmetry, this isn't even something that has to be discussed. The model is already built with the awareness that this cube and any rotation is still the same cube. So it's very helpful. You can end up, you don't need to train as big of models, you don't have to train as long. Your model doesn't even have to be as big to still represent a huge amount of information. And so you also have the guarantee with symmetry that if I rotate my sample a little bit, that prediction is stable. So it's nice and smooth. Okay, so one of the things I work on are Euclidean neural networks, and so these are equivariant models that have Euclidean symmetry, so 3D rotations, 3D translation, and inversion. Inversion is what gives you things like mirror planes, screw axes, glides, things like this. So this is all built into the model, and these networks understand that a physical system described by different coordinate systems still means the same thing. And this can be really handy, particularly if you're dealing with complex properties of atomic systems. So on the left, I'm very bad at left and right. So on the left, we have a simple water molecule that's just simply rotating, simple 3D rotation. And on the right, I have a representation of its Hamiltonian matrix. So this is the matrix that's describing the favorable or unfavorable interactions between electrons in different, in this case, local atomic orbitals. That's the basis I've chosen for representing this matrix. So for example, these are the orbitals on the oxygen atom. So we've got S, orbitals with different radial functions, p orbitals, a d orbital, and these would be the interactions of the oxygen orbitals with themselves, and these would be the interactions across hydrogen and oxygen. And so this rotation might be simple, but the rotation of these elements of the Hamiltonian matrix are not very simple. Certainly a interaction of a d orbital with itself will scale like a fourth order polynomial. You don't really want your model to be spending time learning rotations, which we know very well. You'd much rather have it spend its time learning about quantum mechanics. So just to be a little bit more concrete, because this question's come up a lot, okay, what is the inputs and outputs of your model? So in this particular case, when we're learning on atomic systems, this can change depending on the representation of your data. We tend to give the geometry and the features on this geometry. So if I'm dealing with atomic systems, it'd be where are the atoms and what types of atoms are they, or what are their velocities? Are they experiencing any forces, anything like that? So in this case, I have maybe 2 point masses. So they both have a mass, which is a scalar quantity, and they both have acceleration and velocity vectors, so 2 vectors. So I have my geometry, this is where they are in 3D space. I have the mass, the velocities, and the accelerations. Another really important thing when using symmetry equivariant neural networks is that you need to define what this data is. How does it change when I change my coordinate system? So a mass doesn't change. If I rotate my coordinate system, it's a mass, it's a scalar quantity. But a vector does change. And so additionally with these networks, you not only specify geometry and features, but what are the features? You need to tell the network what symmetry is in the system in order for it to preserve it. So that's kind of a very quick introduction to that. Any quick questions on that? Otherwise, I'll keep going. Cool. How am I doing on time? Good. Perfect. Okay, so I want to show you some applications. This is pretty high level, so I'm happy to answer any questions about the details. So we've been using these Euclidean neural networks to build data-efficient and scalable models of complex physical systems. So just to kind of give one example that gives maybe some context for how quickly the field's been changing recently. So these models are currently state-of-the-art in terms of accuracy for ab initio machine-learned molecular dynamics, so very much related to the previous talk and many other talks. So this is the idea of let's take a very expensive quantum mechanical simulation and emulate it with a machine-learned model so that we can scale these insights to larger systems, more complex systems, basically to give our supercomputers a bit of a break because these systems would not be computable within a PhD thesis. So in December 2020, DeepMD, which is a team that had many members at Berkeley Lab, but also other places, were awarded the Gordon Bell Prize, which is sort of the Nobel Prize of supercomputing. And this was a big deal because I believe it was the first time that it was awarded to a machine learning effort. So kind of a big deal of scientific computing and machine learning kind of getting this big prize. And they were awarded it because they scaled this like ab initio molecular dynamics to 100 million atoms. So quantum mechanical accuracy on 100 million atoms. Now using the Summit supercomputer, which has 27,000 GPUs, so not only a big scientific effort, but also a huge engineering effort. So it was super cool. So with my collaborators in the Kaczynski group at Harvard, we put out shortly after this model NEquip, which under the hood is using Euclidean neural networks and our software package E3NN for implementing these. And basically was able to show that we could achieve the same level of accuracy as DeepMD with 1,000 times less data. So the specific data set I'm discussing for this metric is they were training water molecular dynamics, and the original training set that DeepMD used was 100,000 examples, and we got superior accuracy with 100 examples. So it shows you a bit on how data efficient you can potentially be in certain cases. So more recently, Allegro came out, and so this is also with Boris, and this is all them. It's a great model. And basically they're showing that we could also be as scalable as methods like DeepMD. So they were able to scale these equivariant neural networks to 100 million atoms. In this case, only using on the order of 100 GPUs. Now, there's also a lot of details there. But so this is just showing that like these methods are effective and they're scalable and they're very data efficient. And all the codes are open source too. So there's a lot of opportunity to build upon these methods and make them even better. We've also started using them to kind of use them to answer scientific questions in kind of fun ways. So this is a work that's led by my friend Josh that I got to work on with him. And we wanted to see, could we ask the question, like, what is the nearsightedness of water? Now, the answer to that question isn't necessarily new, but the way we went about answering that question was a little different. And so what we did is we wanted to basically see, let's say I want to predict the forces of a cluster of water molecules that's like 30 water molecules. But I only have data of smaller water molecules. How effective can my model be if it's only trained on smaller clusters? And then we did this for density functional theory data, and then we also did this for coupled cluster to look at the accuracy. And so what we're basically saying is, okay, let's parameterize this model and see, when does the training line kind of converge here? So in this case, we're seeing that once you get to about 10 water molecules, the accuracy gain starts to kind of slow down. So it kind of gets the majority of the idea of what to predict for the 30 cluster once you get to about 10 or 12. So just kind of saying, like, you can actually start articulating scientific questions. More recently, this is the first paper coming out of my new research group. So this is my grad student, Elon, and he made this really awesome model that it's not yet the top of the leaderboard for the open catalysis data set. This is a data set put out by Facebook and also CMU for basically, question, yeah?
Sorry, just curious on the previous plot, the error that it is asymptoting to.
Yeah.
Yeah. Where is that coming from?
Oh, the percentage dense electron density error? Yeah, there's actually like a specific way that you kind of grid the electron density in 3D space and then compare. So it's actually a non-trivial metric that I might have to actually check specifically, but it is one that is considered a good metric for electron densities. Or it's the difference between the ground truth electron density. In this case, this is for DFT. We don't have it for CCSDT. So it's just the percentage difference on the density between the ground truth density functional theory 30 water molecule cluster versus what the model predicts.
But okay, thanks. Yeah, I guess I'm asking the reason the model doesn't keep getting better is there some irreducible problem with the model that like adding more molecules is not able to help with?
I'm not sure. I'll think about it.
Oh, thanks.
Yeah.
Sorry.
No, it's a great question. Yeah. Yeah, it might be an expressivity issue, possibly. Yeah. Okay, so yeah, just saying that these models can be effective on different types of tasks. In this case, it's what is the energy, what's the binding energy of a small molecule onto a catalytic surface, so some sort of alloy. And so what's really kind of fun about this is that Elon's training most of these models on 2 GPUs, and then the top kind of leaderboards, these are very large models, trained by Fair and NERSC. And so, once we are able to scale up this equiformer model, I'm really curious to see how it does. These are also trained on, I think, about 100 times more data, because there's different ways you can divide the data set. So it's exciting that we're even able to kind of play ball with these bigger networks, mostly from our choice of architecture. This is not, I'm not affiliated with this at all. I just think it's super awesome. So folks from the Drawer Lab have, this is at Stanford, have used our code framework to basically predict RNA structures from only 18 examples of RNA structures. So great generalization, 81% accuracy on unseen structures while trained on 18 small structures that were characterized before 2007. And so that's just kind of a really fun thing. I love it working with people with our code base, but it makes me even happier when people are able to use our code base on their own. I probably am running out of time. I wanted to make a quick slide about something that was mentioned yesterday about the power law slope of invariant, so no coordinate system, versus equivariant, keeping the coordinate system models. And effectively, the offset will depend on your architecture, but whether you've turned on kind of vector quantities tends to make the slope change drastically. And this is not necessarily task dependent. So here's just a flash of some of the different papers coming out who have seen this. So other people are saying this too. So when in the case of electron densities, where we not only have vectors, we have d orbitals, so high order things, we do see that, again, the slope isn't changing too much, but we do get a good offset from higher order features. And then I think I'm probably out of time. Okay, I'll wrap up. Unexpected properties. These models are symmetry preserving. If you put in high symmetry data, your outputs are going to be high symmetry as well. So if you give it a tetrahedron or an octahedron, it will automatically output things that have the same symmetry. And this is actually what physical systems do too, unless you have some sort of symmetry breaking mechanism. And this can show up interestingly in training tasks. So if I ask one of these models to deform a rectangle into a square, it can do the task. But if I ask it to deform a square into a rectangle, it can't. So if I ask it to predict the distribution of prediction vectors, basically it can predict to distort this point to the square. But in the case of this problem, even though I only showed it one rectangle to distort to, it is able to infer that there's actually two degenerate solutions. And so this is when your model tells you that the task you proposed was ill-posed. And there's various ways you can kind of go from here to resolve this, but I think this is really interesting because these models can actually check what we're doing. So I'll just leave this up, and I'll take any questions.
It's a great talk. So can you go back to your plot when you see the difference between with the symmetry, without symmetry training?
Okay, so I think I only have ones with invariance versus equivariance.
No, just go back to your illustration. Yeah.
Oh, okay.
Yeah, this one.
Yeah.
Okay. So okay, you interpret it as a way of saying that having symmetry input, you can train it faster with smaller number of sample.
So again, both of these models have symmetry, but basically if you have the full geometric information,
Okay, yeah.
you can learn quicker.
Right.
Yeah.
So I would like to interpret it differently.
Sure, go for it.
I would like to interpret that the yellow line, if you continue the trend, it will get the same accuracy or a low error, but it will discover the symmetry that you're missing.
What do you mean by discover the symmetry?
I mean, when you eventually you train to the point, when you reach enough, this is actually going back to the answer that Arena gave to, the question Arena asked is that if you are dumb, we are innocent, we don't know the symmetry to start with, but if we have seen enough samples, and the training long enough with a large enough model, we do it slowly,
So
but eventually we'll get the accuracy, and by that the same accuracy. By that time, if you look at your answer, the symmetry is actually in the answer that you discovered.
So I would agree for a traditional neural network that has no symmetry, but for something that's invariant, it's actually a stricter subclass of parametric functions, and so there are certain interactions that are impossible for it to represent.
Okay, because also this is related to David's problem of rotation. I was thinking if somebody used the equivariant, if somebody used the equivariant network to actually look at the rotational MNIST, would they get a better performance than the 60%?
They should, by definition, get a perfect score.
Okay, here's a try it.
I mean, yeah. I mean, that's what we do that's our unit test for our code base. We actually have it classify 3D Tetris pieces, and we show it only in one orientation, and then you show it any orientation, and it has to get 100%, otherwise we broke the code. So it's our unit test. But maybe, unless I'm misinterpreting the task. Hi.
I have a basic question.
Sure.
What is the difference between your model and a graph neural network or relational network? I mean, they have somewhat similar ingredients.
Yeah, so I mean, there's quite a zoo of neural networks out there, and there's a lot of kind of names for the same concepts in different contexts. So you can certainly parameterize our models as graph neural networks. The concept of equivariance can be applied to voxels or meshes, like any type of representation. Yeah, yeah.
They
Yeah.
have the same symmetries.
Yeah, yeah, exactly. So basically, if you're in 3D Euclidean space, this should work for you.
Okay.
Yeah.
At the age of scale, it's great to see that bigger is not always better. Quick technical question. In terms of the evaluation, like flops,
Yeah.
how far it's more expensive? Things like model we develop, like
Yeah. We're
you know,
definitely more expensive
invariant.
than you. Yeah, but
Is it 10x, 50x, or
you know, I don't know off the top of my head because like you have to get someone to make a table
Okay.
as like the same architecture. Certainly, there have been some recent changes to the repository that's made things a lot faster. Like we compile down with TorchScript a lot better now. So I don't have a good answer for you. It also depends on the model size. But Allegro is not a message passing network, and that's what really allows.
and
it
you
to
can
scale.
combine with message passing as well.
Yeah, so basically Nequip is a message passing network, but Allegro is showing that if you just have a cutoff radius, for a lot of things you can do just
Okay,
as well.
yeah, makes sense. It's faster.
Yeah,
so-
and that's how you're able to get the scale. Message passing, you're just not going to be able to, MPI is going to be really unhappy.
Hi, very nice talk. I just wanted to add something that I don't think you commented on, and it's a very nice property that I think you should emphasize. You were saying that one of the advantages of building in this equivariance is that it's more data efficient, and I think you emphasized that. But from the perspective of physical simulations, we carefully construct numerical algorithms to strictly satisfy certain conservation laws, certain symmetries, and so this is, I think, critically important in that context. So, and it seems that you've applied it in this context, right?
Yeah. Although I want to make sure the difference between a conservation law symmetry requires time. So we're not doing Noether's theorem, but certainly like.
I understand.
Yeah.
But still, when it comes to, for instance, calculating forces or something like that, guaranteeing that you've got this right is, I think, a great advantage. So you've applied this a lot to atomistic systems. Do you know of any examples of trying to apply this to continuum systems?
Yeah, so I'd love to see more in this area on that, so maybe we should chat more about it. I know my postdoc's currently applying it to MRI data, and that's been pretty interesting so far. But I think mostly it's just a matter of like, my background is in condensed matter physics, and so I've been dealing with atoms, but there's some details. Robin and I have been talking about bandwidth limiting on the filters and things like that. So there's some nuances to applying it to discretized data, but you can also do it for meshes. But yeah, I'd love to see more folks using it in different domains. I'm sure we'd learn a lot. Thanks.
Oh, okay, one last question, and in the meantime, we'll do a transition to the next talk. Yeah, go ahead.
Yeah, I was just wondering if you could speculate on the like no symmetry line on the schematic plot that you drew. Like if you were to add it, like if you had a guess for what it would look like. You had the invariant.
I see what you're saying. I think the slope would be pretty slow. I don't have a numerical value for that.
Like worse than the invariant, you're thinking?
Oh yeah, definitely. Yeah, definitely worse than invariant. It's a very useful prior because otherwise like coordinate systems change pretty rapidly in 3D. So, okay, thanks.
Okay, thank you, Tess. And